10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Hello student, good evening to all of you once again here in our this online learning lecture. So today we are going to start our new chapter, chapter number 9, areas of parallelogram and triangle. So we have already complete our chapter number first to 8 and chapter number 15, and all keys are available on our this channel. So if you want to see any of chapter or any of points of any chapter, then you can easily see. I have sent it in our mass group. Okay, so now today let us start our new chapter, chapter number 9, areas of parallelogram and triangles. So first, introduction. In chapter 5, you have seen that the study of geometry originates with the measurement of earth or lands. In the process of recasting boundaries of the field and dividing them into appropriate parts. So for example, a farmer Budia had a triangular field and she wanted to divide it equally among her two daughters and one son. That means three. Two daughters and one son. So without actually calculating the area of the field, she just divided one side of the triangular field into three equal parts and joined the 2 points of division to the opposite vertices. See here like this. This triangular field and one side divide into two equal parts. 1, 2 and 3. Okay, and join the opposite vertices. So in this way the field was divided into three parts and she gave one part to each of her children. Okay, so do you think that all the three parts so obtained by her in fact equal in area? To get answers of this type of questions and other related problems, there is a need to have a relook at areas of plan figure which you have already studied in earlier classes. So you may recall that the part of the plane enclosed by a simple closed figure is called a planar region corresponding to that figure. A part of the plane enclosed by a simple closed figure is called a planar region corresponding to that figure, and the magnitude or measure of this planar region is called its area. So magnitude or measure of planar region is called its area. This magnitude or measure is always expressed with the help of a number in some unit such as 5 centimeters square, 8 meters square, 3 hectares, etc. So we can say that area of a figure is a number or in some unit associated with a part of the plane enclosed by the figure. So we are also familiar with the concept of congruent figures from earlier classes and from we have already studied in chapter number 7. So two figures are called congruent if they have the same shape and the same size. Two figures are called congruent if they have the same shape and the same size. Important. Shape is same, size is same. See here. Here two figure A and B. Both are congruent. Let us see. See here. Let us check. These two figure A and B both congruent figure. So we can check same size, okay. Now see here. In other words, if two figures A and B are congruent, then using a tracing paper, you can superpose one figure over the other such that it will cover the other completely. So if two figures A and B are congruent, they must have equal area. However, so this is important. So if two figures A and B are congruent, they must have equal area. However, the converse of this statement is not true. What is converse here? In other words, two figures having equal area need not to be congruent. Okay, let me repeat it. If two figures A and B are congruent, they must have equal area. But if two figures having equal area need not to be congruent. For example, this is important. See here, for example, so in figure rectangles ABCD and EFGH having equal area 9 into 4 centimeters square, which is rectangle, 6 into 6 centimeters square, which is square, but clearly they are not congruent. See here, 9 into 4 centimeters rectangle, so area is 36 centimeters square, and another one is 6 centimeter into 6 centimeter, so 36 centimeter square is area. So area is equal area, but these two figures are not congruent. Now see this figure. See area P, area Q and area T. So see here, observe that this planar area formed by figure T, this planar area is formed by figure T, is made up of two planar regions formed by figure P and Q. Figure P, one area, figure Q, another area. So you can easily see that area of this figure T is equal to area of figure P plus area of figure Q. Again see, area of figure T is equal to area of figure P plus area of figure Q. It's easily understandable. So you may denote like this: area of figure A is equal to AR into bracket capital A, area of figure B as AR into bracket capital B, and area of figure T as AR into bracket capital T, and so on. So with this notation, you now can say that area of a figure is a number, some unit associated with the part of the plane enclosed by the figure with the following two properties. So these two properties is important. First one, if A and B are congruent, figure A and B are congruent, then area of A is equal to area of B. And second one, if a planar region formed by figure T, like this, then is made up of two non-overlapping planar regions formed by figures P and Q, then area of figure T is equal to area of P plus area of Q. These two properties are very important here. So you are also aware of some formulae for finding the areas of different figures, such as you have already studied in your earlier classes: rectangle, square, parallelogram, triangle, etc. Okay, so in this chapter, attempts shall be made to consolidate the knowledge about these formulae by studying some relationship between the area of these geometric figures under the condition when they lie on the same base and between the same parallel. See here. See here, what new? Some relationship between the areas of these geometric figures. Which geometric figure? Square, rectangle, parallelogram, triangle, whatever. Under the condition, this condition is very important here, they lie on the same base and between the same parallels. What is the same base? What is the same parallel? Let me see. This study will also be useful in the understanding of some result on similarity of triangles. So now Next one is figures on the same base and between the same parallels. See here. Parallelogram and trapezium. ABCD trapezium, EFCD parallelogram. So in this figure, trapezium, ABCD and parallelogram EFCD have a common side DC. Again, this is the common side for both trapezium and parallelogram. Trapezium ABCD and parallelogram EFCD both have a common side DC, and we say that trapezium ABCD and parallelogram EFCD are on the same base DC. So what is same base is important to understand for you for this chapter. So try to understand here. CD or DC is the same base for trapezium ABCD and parallelogram EFCD. Okay. Now see this figure. PQRS, MNRS both are parallelogram. PQRS and MNRS. Now similarly here also in this figure, parallelogram PQRS and parallelogram MNRS are on the same base SR. So SR, in other words, SR is the common side of both this given parallelogram PQRS and MNRS, or in other words we can say that both parallelogram PQRS and MNRS are on the same base SR. So next, see this. Two triangles ABC and DBC. Two triangles here ABC and DBC. See here. In this figure, triangles ABC and DBC are on the same base BC. Now see here. Triangle ABC and triangle DBC have a common side BC, that means they are on same base BC. Now parallelogram and triangle. Parallelogram is ABCD, triangle is PCD or PDC. Clearly, DC is the common side or same side. So in this figure, parallelogram ABCD and triangle PDC are on the same base DC or common side DC. So this using this fourth figure, okay, same base, lie on the same base and between the same parallel. So these four figures are useful to understand what is same base. Here CD is same base, here SR is same base, here BC is same base, here DC is same base. So this is important to understand same base of two given figures, maybe trapezium and parallelogram, maybe both parallelogram, both triangle, triangle and trapezium, triangle and parallelogram also. Okay, now look at the following figures. Now see here. A, B, C, D. Try to understand what I am telling to you. A, B, C, D, trapezium. E, F, C, D, parallelogram. A, B, C, D, trapezium. E, F, C, D, parallelogram. Now, it is clear that CD is the common side or same base for trapezium and parallelogram. Okay, see here, I will come back on this figure, but see here first. In this figure, trapezium ABCD and parallelogram EFCD are on the same base DC. ABCD, trapezium, EFCD, parallelogram, same base CD. So, okay. Now, in addition to the above, the vertices A and B of trapezium ABCD opposite to the base DC and vertex EF of parallelogram EFCD opposite to base DC lie on a line AF which is parallel to DC. This is important. See here. The vertex of trapezium ABCD. So A vertex A, B and for parallelogram E and F are lie on the same line and which is parallel to this side DC. In another word, the line AF is parallel to DC. So this is like this here. A, B, C, D trapezium, and I think here is E, F. This figure is like this. So the trapezium and parallelogram EFCD lies on same base CD. Base is common. The base of this parallelogram is CD, EFCD and ABCD. So CD is common side or same base. And parallel to CD, this line AF. So vertex A, B, E, F lies on the line which is parallel to the common base CD. This is important. So see here. So this is common. So this point is very important. In addition to the above the vertex A and B of trapezium ABCD opposite to the base CD or DC and vertex EF of parallelogram opposite to base DC. So ABEF are lying on a line AF which is parallel to DC, and we say that trapezium ABCD and parallelogram EFCD are on the same edge DC and between the same parallels AF and DC. So this concept is very important. When we can say that trapezium ABCD and parallelogram EFCD are on the same base and in between the same parallels, a figure like this. So in this figure, trapezium ABCD and parallelogram EFCD are on same base and in between two parallels CD and AF. Now see this figure. So two parallelogram PQRS MNRS. First one is PQRS and then MNRS. Let me show you PQRS. This one PQRS and MNRS. It is clear that this is common side SR for both this given parallelogram, or these both parallelogram are on same base SR. See, now in this figure, parallelogram PQRS and parallelogram MNRS are on the same base SR. And between the same parallel PN and SR, again see the figure, and between the same parallels PN and SR, see PN and SR are parallel. So as the vertices P and Q of PQRS, M and R of MNRS lie on a line PN parallel to base SR. Try to understand. This is important. Vertice PQ of parallelogram PQRS and vertice MN of parallelogram MNRS R lies on the same line PN, and this line PN is parallel to the same base SR. Then you can say that these two parallelograms are on the same base and in between same parallels. Now again, see this figure. So two triangle ABC, triangle DBC. Again ABC and DBC. Now you all are clear that these two triangles are on the same base or common side BC. See, in the same way in this figure, triangle ABC and triangle DBC lie on the same base BC, and between the same parallels AD and BC. So see here, A is the opposite vertex of the common side BC or opposite vertex of same base. Opposite vertex of same base BC. A and D lie on a line, which line is parallel to the same base BC. And that's why we can say that these two triangles ABC and ABC are in between two parallels and having same base. Now see here, this is very interesting also. ABCD parallelogram and PCD or PDC triangle. First, see this figure careful. ABCD parallelogram, PDC or PCD is triangle. Okay, but see this. The side DC is common for both parallelogram and triangle, or we can say that this parallelogram and triangle are on same base DC. Moreover, the vertex of parallelogram ABCD and opposite the same base DC is A and B, and vertex of the opposite side of same base of this triangle is P and C. Here AB and P lies on the line which is parallel to the same base DC. So AP and CD are parallel. See here. In this figure, parallelogram ABCD and triangle PCD. ABCD and triangle PCD lie on the same base DC. lie on the same base DC and between the same parallels AP and DC. Between the same parallel AP and DC. So, two figures are said to be on the same base and between the same parallels if they have a common base or side and the vertex of the vertex opposite to the common base of each figure lie on the line parallel to the base. Then we can say that these two figures are on the same base and in between the same parallels. So, okay, this is important point when we can say that two figures are on the same base and in between the same parallels if they have a common base or common side and the vertices or the vertex opposite to the common base of each figure lie on a line and which line is parallel to the base or common base, then we can say that. Okay, so these all are important points. Try to revise it and try to understand. This is very important for our further study of this chapter, and with this now we are going to end our this today's lecture and we will meet you in our next lecture. Okay, till then, goodbye to all of you once again. Good evening. Okay, student, bye.